Good evening to all. In the last class, that is yesterday, we discussed how to verify the Ohm's law in the Tinkercad, and also the Kirchhoff's laws, that is the KVL and the KCL. Let's see. Uh, Once again, those two circuits, just the simulation, and we'll see some the digital circuits also today. This is the simple circuit who were not there yesterday. This is the Ohm's law, and this is the Tinkercad, the circuit diagram. This is a power supply, so we try to vary the voltage. Sorry, we try to vary the voltage in the RPS, and here in the RPS we try to vary the voltage, and note on the current in the millimeter and the voltage across the register. Okay, so the voltage across the register depends on the value of the resistance, and also the current depends on the resistance value. So we saw the variation of the resistance, the power supply, and all. Next we saw the diode circuit also, and KCL as well as the KVL circuit also. Let's see for a moment. Just we'll go for the Tinkercad, and we'll see a couple of digital circuits today. Well, this is the Chrome. From here, yesterday I shown you how to log into Tinkercad. Just you can type Tinkercad in the Google Chrome also. Otherwise, in the Google search also, that's fine. Just give Tinkercad. So it will be, as I said, it will be a little slow because now we will see this page, and here click on the sign in, click on sign in with Google. With any of your Gmail ID, you can log in into the Tinkercad. So this is, it lost the Gmail ID. Since I have logged in, so I'll reach my home page. Okay, so here we see the different circuits. As I said in the beginning, this Tinkercad can be used to design the 3D circuits and animations and all. Now here we're going to practice the circuits. So click on the circuits. So once you click on the circuit, so these are all the circuit diagrams what we have discussed before, and recently used circuits will be in the beginning. So let's see the Ohm's law once again. Now need not to build again. Okay, simply once the circuit is there, just you tinker this and it will open. Yeah, fine. So this is the diagram. I shown you how to build all these the circuits and all. Go for the circuit simulation. So this is the 2 volts. Now the resistance value is the 100 ohm, because the color code is the brown, black, and brown. Okay, the voltage is 2 volts. So this voltage will appear across the register. So 2 volts by 100 ohm gives a current of 20 milliampere. So current is 20 milliampere, and the voltage of the resistor is the 2 volts. Whatever you apply across the power supply, the same voltage will appear across the register. So you can change the register value. Just to click on that, you can type the value of the register. 220 I do. So 220, the color code is what? The red, brown. Okay, so red, brown. The digit for the red is what? 222. Last band is the brown. Last band is the brown. 10 power 1. The brown is 1. 10 power 1, which is the multiplier. So 22 into 10 power 1, that is 220 ohm. Again, if it is 2 volts, or if you calculate 2 volts by 220 ohm, you'll get 0.09 ampere. So if you convert into milliampere, it is what? 9.09 milliampere. So you can vary the voltage using this knob also. Okay, you can see the variation. Otherwise, you can set a particular voltage. Say for example, I want to set it for the 4 volts. Just you click on the RPS, remove this and type 4. That's all. So it's 4 volts now. So 4 volts is going to appear across the registers. Is showing in the voltmeter, and 4 divided by 220 is what? 18.2 milliampere approximately. So we'll get the almost the same values what we get in the lab, the real-time components. This is the Ohm's law. Now we'll go for the Ksl and Kvl. This is the KVL, Kirchhoff's voltage law. Here we're going to use 3 resistors. This is a 100 ohm, this is a 2 kilo ohm, and this is 3 kilo ohm. Okay, so accordingly the color codings, for the 100 ohm is the brown, black, brown. For 2 kilo ohm, the digit corresponding to red is what? 2. This is the red, black, and orange. Okay, that is a 2 kilo ohm. And the third one is a 3 kilo ohm. So if you want to change the resistance value, just to click on those particular register as we discussed. This register, I can change it as say 220, doesn't matter. 220. I'll make it as 330. 330 ohm. Let's make it as ohm. It's in kilo ohm. So it is a 470. Let's do it. 470 ohm. I'll do. Okay, 470. Accordingly, you can see the color coding also. That will be right. Now we'll go for the let's set the voltage, say for 2 volts, for example. The 2 volts. So go for the simulation. Say applied voltage is what? 2 volts. This is V1, this is V2, this is V3. Let's call it as R1, R2, and R3. The registers. The voltage across the first resistor is what? The V1. The voltage across the second resistor is what? V2 and V3. So you can see now all these are in millivolts now. If you convert them into volts, the first one is what? 0.431 volts. The second one 0.647 volts. Last one 0.922 volts. So if you add up all these things, it will be equal to the applied voltage. So from the Kirchhoff's voltage law, you can define it as in various ways. In a closed circuit, this is the closed circuit now. So we start from the positive of the power supply. This is the closed circuit or the loop, what we can say. The applied voltage is equal to the sum of the voltage drop across the voltage drops across the individual register. Okay, or the algebraic sum of all the IR drops and the EMFs in a closed path is equal to 0. So we try to define it various ways. In a simple way, this applied voltage must be equal to the voltage drops across R1, R2, and R3. So if you add up all these things, we will get the approximately the 2 volts. So if I change this, okay, I try to change this voltage now. Let's make it 6 volt. So we can see now, if you add all these voltage, it will be around the 6. So which is the Kirchhoff's voltage law. Okay. Now once you build it, you can, as I said in the yesterday class, there will be some random name will appear for the circuit what you design. We can change it as KVL. Okay, so you can give any name. Takes a small amount of time. It's fine. So now, once the circuit is done, the simulation is done. Stop this simulation and click this blocks. There is a Tinkercad block. You'll see the home page. Now let's try to the KCL, Kirchhoff's current law. Tinker this. Okay, so see the circuit diagram. I'm going to use a single power supply, RPS, and this is the one register. Let's call it as R1, and this is R2, and this is R3. In this case, all these are 1 kilo ohm. If you click on the register, you will see its parameters in the blocks. So this register is, the resistance is what, 1 kilo ohm, and this is R2. So again, it's 1 kilo ohm. This is R3. Is also 1 kilo. We can change the resistance values also. Let's see it later. Now this multimeter is going to be used as the millimeter. So millimeter 1, it is a we can say the A1. This is ammeter 2, and this is the ammeter 3. Okay. Now let's go for the start simulation. See, now it is the 10 volts. Now due to the total circuit in the total resistance in the circuit, this resistor is in series with the D star parallel combination. So it is a 0.5 kilo ohm, we can say. This is 1 kilo ohm. So total is the 1.5 kilo ohm. So the 10 volts divided by 1.5 kilo ohm gives, this is the main current, that is a 6.67 milliampere. That will divide equally because the resistances are the same. This was 1 kilo ohm, this was 1 kilo ohm. So this current, which is a 6.67 milliampere, is going to divide equally through this resistor as well as this resistor. So it is, you can see both the millimeters are reading 3.33 milliampere, 3.33 milliampere. Now I'll try to change this, the value of the resistance. I'll make it as, say, 2 kilo ohm. So as soon as you change the value, so it is 6 milliampere. This is the main current. So this is the one branch current, this is the another branch current. So we can call it as I1 and this is I2. So let's call this main current as I. So I is equal to what? I1 plus I2. So need not to define the KCL. So what is KCL? How we define? The algebraic sum of the currents meeting at a node. This is the node where all these components are or the branches are meeting. The branch 1, branch 2 and branch 3. Okay. So this is at this node we can apply the KCL. As we know, we can apply the KCL at a junction or the node. Node is nothing but there is a junction where the two or more branches meet. At this node, this branch and this branch and this branch is also the meeting. So at this junction, so we can apply I1 is or I is equal to I1 plus I2. That is 6 milliampere is equal to this current 2 milliampere plus 4 milliampere. So sum of these two will be the same. So if I change this register, say 10 kilo, I'll make it as 10 kilo. So you can observe. So if the resistance is more, the current will be less through that. So this is 10 kilo, and due to the increase in the resistance, the total current decreased to 3.75 milliampere. This 3.75 milliampere will divide as the I1 and I2 through these two branches. The sum of these two must be equal to this current. There is a 3.12 milliampere and 6.25 milliampere together must be equal to 3.75 milliampere. So at any moment at this junction, the sum of these two will be always equal to the main current. Okay, that is what the KCL, Kirchhoff's current law. Fine. Now let's go for the digital circuit. So diode characteristics also we have seen in the last class. So we can make it as either the forward bias or reverse bias. In forward bias, we saw in the last class, the current start to flow after the knee voltage. That is 0.7 volt for silicon diode, 0.3 volt for germanium diode. Okay, these are the simple circuits. So we'll see some of the digital circuits today, and later I'll discuss those analog circuits. So the digital circuits mentions basically the logic gates. The logic gates are the building blocks of any digital system or the computer, we can say. So we know the classification of the logic gates as the basic gates, the universal gates, and the hybrid gates. The basic gates are what? NOT gate, OR gate, and AND gate. And the universal gates are what? NAND gate and NOR gates. The hybrid or derived gates are what? The XOR gate and XNOR gates. So as we know, the Boolean equation for the AND gate is, say, Y is equal to or C is equal to A dot B. Okay, and in case of the OR gate, Y is equal to or C is equal to A plus B. Okay, in case of the NOT gate, the output Y or C is equal to, you can give any name, the variable name A, B, C, or X, Y, Z, whatever it is for the inputs and the outputs. And for the NOT gate, C is equal to or Y is equal to the complement of A. That is A complement we say, otherwise A dash we call it as. For the NAND gate, so as I said, Y is equal to AB, A dot B. That is A dot B. So the possible combinations for the two inputs. As we know, a logic gate may have n number of inputs, but a single output. A logic gate may have n number of, that is 3, 4, 5, 10, 20,000 inputs may be there. Doesn't matter, but only one output. Okay. The same way here OR gate may have either 2, 3, 4 any number of the inputs, but a single output. But the exception is what? The NOT gate. It has a single input and the single output. So if you call the input as A the output will be what? Complement of that. And as we know, there is a meaning for these. So we call these as the gates. So calling them as the gate in a sense. So it allows, these circuits will allow the output to go to high under certain conditions which meet at the input. So usually, uh, a security person at the gate, what he does, he won't allow all the visitors. He will check certain conditions, okay, with the visitors. If he is valid, or if he is going to satisfy the, if he is able to give the satisfying answers for the security person, then only he allows. So there is a meaning to call these circuits as the gate. So these gates will allow the output to go to high only at under certain conditions which meet at the input side. So for AND gate, if the output has to be 1, all the inputs must be high. Otherwise, it will not allow the output to go high. So in this case, both should be high. Then only C will be high. So you can observe now, as we know. So many of us know it. 0 0, the possible combination what both may be 0 0 or 0 1, 1 0, 1 1. So the output is 1 only when both the inputs are high. So there is a significance of calling this as AND. Why we call it as AND? The output is high when A is high and B is high. In the same way, the OR gate. So in case of the OR gate, as the name indicates, it's OR means what? The output is high when either A is high or B is high, or maybe both high, doesn't matter. But the condition is the one of the inputs must be high, either A is high or B is high. This in case of the 3-input OR gate. So A, B, C, like for example, or the inputs, and Z or X is the output, for example. Okay. So all the three, out of all the 3 inputs, any one input must be high in case of the OR gate, so that the output will be high. You can see in the first case the output is 0 because both the inputs are 0. But in all these cases, other 3 combinations, the output is high because so one of these 2 inputs is 1, or both may be 1, doesn't matter. Okay, so we call it as the OR gate. In case of the NOT gate, is what? The output is not the input. The possibility is what? Only either high or low. Okay, the possibility is either high or low. So if the input is low, the output is not low. What it must be? High. Very simple. And if the input is high, the output uh, is not there. High is nothing but 0. So the name, the NOT gate. So using these basic gates, so we can build the NAND gate and NOR gates. NAND is the combination of the and NOT. Okay, and NOR is the combination of OR and NOT. Okay, so we can see those later. Okay, fine. This is a circuit for the NOT gate. Okay, it is going to act like a switch. Okay, the transistor as a switch is nothing but the NOT gate. If you apply the A is 0, the output Q or Y or C, what we can call it any names, doesn't matter. Okay, here in the circuit is what? The Q is equal to the A bar. It should be A bar, not the Q bar. Okay, should be actually we use the Q, and the Q bar is what in case of the flip-flops and all. But in this case, we can call this as the A bar. We can write Q is equal to A bar. So an NPN transistor is going to be used. Okay, and here if you apply the input is 0, as we know in the last class also, for all the digital circuits we apply either 0 volts or the high voltage. High voltage means 5 volts. So in most of the logic circuits, we use the only 2 voltage levels. There is 0 volts and the 5 volts. 0 volts is going to be considered as the low, and the high voltage is going to be, that is 5 volts, is going to be considered as the one in case of the positive logic. In case of negative logic is exactly the reverse. So once we apply the A is equal to 0, the EB junction is a NPN transistor now. This is NPN transistor, this is emitter, this is the base, and this is the collector. If the transistor has to be on, this EB junction should be forward bias. So EB junction will become forward bias only when this voltage is more than the new voltage. For silicon transistor, again 0.7 is the new voltage. So this voltage must be it is the voltage at A must be more than 0.7 volt. But here we will not allow, will not apply any voltage than 0 or the 5 volts. So if A is 0 volts, so it will not forward bias. So the transistor will be in cutoff. So it won't conduct at all. Since it is not conducting, so when the transistor is on, conduct means it is on. Okay, so the transistor will be either on or off. What we say, in the transistor will be off. When it is off, this doesn't make the short between the collector and the emitter. Okay, so if the very simple concept, this is the VCC. The VCC means it is a DC power supply. The positive, you can observe now, plus VCC, we're going to call it as the plus VCC means the positive terminal of the power supply RPS is going to be connected to this point and the negative is connected to the ground. So between this point and the ground, we are going to apply the 5 volts. So there is a resistor is there, R2, and a transistor. This transistor is going to act like a switch. Okay, it will be on or off. When it is a transistor is on, this is equivalent to shorting from collector to emitter. When there is a short here, from here to here, the current start to flow through this resistor from positive term of the VCC to the negative term of the VCC. So when this transistor will be off and on, that depends on the voltage at A. So if the voltage at A is 0, the transistor will be off because the EB junction is not forward biased. Okay. So when it is off, there is no current flowing through this. Okay. So this acts like an open circuit. Therefore, if you measure the voltage between this point and the ground, so we'll get the same voltage VCC. Okay. The same voltage VCC. Here we apply what? The 5 volts. So 5 volts is going to appear between this point and the ground. Okay. And if you apply the 5 volts here, as we know, in the digital circuits, we apply either 0 volts or 5 volts, no voltage in between. If you apply the 5 volts here, so this 5 volts, this is the closed path now. The 5 volts in the sense between this point and the ground again is understood. Okay. The positive terminal of the, we can use another power supply to apply this 5 volts. Otherwise, a single power supply to apply here as well as here. Okay. So in the circuit, I'll explain the right circuit later, just to try to understand the action of this now. So when it is 5 volts, the voltage between this point and the ground is 5 volts. That 5 volts will drop across this resistor as well as the some voltage between the base and the emitter, that is the emitter base junction. So since this is the higher potential, this is the lower potential, this is 0 potential, 0.7, around 0.7 will drop between the base and the emitter, but the remaining voltage. So in this case, we're going to apply 5 volts here. Out of 5 volts, 0.7 will drop between the base and the emitter. The remaining voltage, 4.7 volts, will drop across this resistor. So this resistor plays a very important role. So this usually this resistor is taken as the higher resistance. Okay, it has to limit the current to the base of the transistor. Okay, and also it provides the path for the voltage drop across it, which is the excessive beyond the knee voltage. Okay, so the knee voltage is enough to for this transistor to conduct. Conduct means it becomes on. Once it becomes on, so I'll repeat once again. When it is the 5 volts, so the EB junction becomes forward bias. It starts conducting. Once it starts conducting, it acts like a closed switch. The closed switch means what? From here to here, there is a short. Okay, so there is short means what? Connecting this point to the ground. Okay, it is a single, acts like the single wire. Okay, current start to flow through this. Okay, therefore all the voltage what we apply, this VCC, will drop across this resistor. But since this point is equivalent to connecting to the ground, the voltage between this point and the ground is what? 0, because this gets shorted. So whenever there is a short, the voltage across the short is always 0. So we applied 5 volts here, but here is what? 0 volts. Before we applied 0 volts, it was off and this was high. So 0 volts, high voltage, and 5 volts, 0 volts. So it acts like what? Did not gate, exactly the not gate. So if the input is 0 volts, output is not 0, it is 5 volts. If the input is 5 volts, the output is not 5 volts, it is 0 volts. So It is exactly the replica of the NOT gate. You can observe now in the truth table, if A is 0, the output is 1. If A is 1, the output is 0 in logical way. Okay. Now you can see the circuit diagram. Here I have used a single power supply, which is the RPS here, and I have used the one slide switch. So this is the point A in the circuit. Okay, so this is A. Okay, and this is the VCC. This is the VCC. The VCC means we have to connect the 5 volts between this point and the ground. Now we can observe now. This is the transistor. This transistor is numbered this one. Okay, as usual, this is the emitter, and this is the collector. This is the base, and a resistor is here. This is the resistor, and this is A. So this is point A. So as I said, we can use the separate power supplies for the VCC and for the power supply at A, or a single power supply. Here I use only single power supply. You can see now the positive of the power supply is connected the one end of this switch, as well as the same to what the VCC point. Okay, this is the slide switch. I can slide it down or the up. When the switch is slide down, the middle point, which is A, is equivalent to connecting to this. That is, this is connected to the negative terminal of the power supply, which is the ground. Okay. At the same time, this emitter is connected to the ground. This is the emitter is connected to the 0 volts or the negative terminal of the power supply. Okay. So here, this is the switch now. This is the middle terminal or the common terminal, what we call it as. Upper side of this 5 volts is there. Lower side of this 0 volts is there. So by sliding it down or up, we can apply either 0 volts or 5 volts to this A. Let's call this as A. Okay. And this only this circuit is enough. This is the extra part. So I have connected one voltmeter. That is a multimeter as the voltmeter, which is connected between the output terminal. If you compare with this circuit, from here to the ground, I have connected this multimeter as the voltmeter. It shows the voltage level. So when the input is 0, what is the output voltage it will show. When the input is 5 volts, what is the output voltage it will show. At the same time, I have connected one resistor and LED just to see the logic level. Okay, so if the output voltage is high, it should be on. If the output voltage is low, it will be off. So just I have connected the resistor here with the in series with the LED. Okay, so the intensity of this LED depends on the current flowing through this. The current through this resistor is what? This resistance value. This is an extra part compared to this left circuit. Okay, so only this resistor, this transistor, this resistor R2 or RC, we can say. This is RB or R. So only these three will form, including this power supply.